So today we're going to start in on section 2.2. This is where we really start getting into the normal distributions. We're going to talk about density curves. And then we're going to talk about what's called the 68, 95, 99, 7 rule, or sometimes it's also called the empirical rule. It's basically a rule that works for any normal distribution. And we'll talk about what that means here in a little bit. So this whole chapter, for the most part, is going to be based on this idea of a normal curve, a normal distribution. So making calculations, finding percentages, calculating percentiles, finding area under the curves, things like that. So the first thing we have to do is talk about what density curves are. So a density curve is a model of a distribution. So it's not the exact distribution itself, it's a model of it. It's an estimate of the overall distribution. So if you look at the picture there, you have a histogram. So we have these yellow bars here. That's our distribution, okay? Now the red line would be what our model would look like. That's considered a density curve. So a density curve is going to be a smooth curve that estimates an actual distribution. Okay, so it's not going to be an exact match, but it's going to match it fairly closely. Now, there are two things about density curves that we need to make sure we always know. First is already up here. The area under your curve is always going to be 1. So if you were to look at the entire area underneath a density curve, it is always going to add up to 1. Okay? Now, density curves can come in many different forms. You can have kind of this smooth curve like this, like looks a little symmetric, things like that. You can have uniform distributions, and that's something we haven't really talked about yet. We had symmetric, we had skewed, but there's also this idea called uniform distributions. So a uniform distribution, if we were to look at rolling a die. So when you roll a die, how many different options do you have? 6 different options. Now if I sat there and I rolled a die over and over and over and over again, what should the distribution of numbers that I roll look like? Pretty evenly distributed, right? I'm not going to sit here and roll, I'm no more likely to roll a 1 than I am a 4 or a 6 or anything like that. So if I were to do it over and over again, I should have about the same number of 1s, 2s, 3s, 4s, 5s, and 6s, right? So if we were to look at that, that would look something like this. Now they're not always going to be exactly the same, but for the most part, it's pretty much flat all the way across. This is what we call a uniform distribution. So there's no peak to it, there's no rise and fall or anything like that. It's just throughout the entire distribution, everything seems to be about the same all the way throughout. Does that kind of make sense? So with uniform distributions, the idea of this density curve, so if we were to take this and we were to actually graph it with a curve, the curve would simply be a straight line that ends at our final point, and we'd be looking at all the area inside here. Okay? So for our dice example, we'd be going from 1 to 6 basically, right? That would be the extent of our distribution. So if my base has a length of 6, what would the height of my distribution need to be to make this area under the curve 1, like all density curves need to be? So the length of my base is 6. What does my height have to be? 1/6, right? So if I was looking at this, the height of my distribution would have to be 1/6. If I find the entire area under this curve, it has to come out to be 1 every time. Now that's whether it's uniform like this, or whether we get a smooth curve like this one here, where it's symmetric or possibly skewed, things like that. The area is always going to be 1. And that's going to be extremely important, because when we get to normal distributions here in a little bit, this idea that the area is always 1 inside is going to relate to proportions, percentages. And we know if we put all percentages together, they always add up to 100% for a total, right? So that's the main idea here. The other thing with density curves is that the area always has to be above the x-axis. So the entire curve has to be positive. It always has to be above that x-axis. Okay? So the main one, the one that I put up, is that the curve, or the area under the curve is 1. That's the key. The other one is, it's got to be above the x-axis, it's got to be positive. Okay? Now, density curves can have pretty much any shape. Whatever shape your distribution is, that's what your curve is going to look like. It's a model of what your distribution is. So it can be symmetric, which is the type we're going to be talking about most often, but it can be skewed. Or, like we talked about on the last slide, it can be uniform. So really, when you're creating a density curve, you're taking your distribution and just fitting a smooth line to it. So it's just kind of an estimate of what the overall distribution looks like. Okay? So let's talk about a specific type of density curve, which are known as the normal curves. These are going to be what we spend the entire rest of the chapter working with, normal distributions. And these are going to play a part in almost everything we do past chapter 2. So almost everything we're going to work with from here on out is going to be dealing with these normal distributions. That's why this chapter is so important. Okay, so we need to make sure that as we go through this, you completely understand what we're doing. We're not going to get away from these really ever. So normal curves are a class of density curve. Okay, density curves can be any shape, symmetric, skewed, uniform, whatever. It just models the distribution. Normal curves are a very specific type. Normal curves are symmetric, they are unimodal, so single peak, and they're somewhat bell-shaped. Like if you look at the x-axis plus the curve, it looks somewhat like a bell. Okay, so you guys have heard probably with standardized tests, things like that, things are on a bell curve, or maybe some teachers curve on a bell curve. You've heard that term before maybe. They're talking about this normal distribution. Okay, now these normal distributions, normal distributions occur naturally in real-world situations all the time. Human heights. If you got a big group of people together, thousands, tens of thousands of people, measured all their heights would generally be normally distributed. You're going to have some people that are shorter, some people that are taller, but most of the people are going to be right around an average height. Okay? Standardized test scores. When they grade tests, so those standardized tests, they make them so that they become a normal distribution. They're normally distributed. Some people are going to score low, some people are going to score high. Most people are going to be somewhere around the middle, the average. IQ scores, again, generally normally distributed. So there's lots of different times where you will run into these normal distributions within real life. And a lot of the times that we're going to, or a lot of the different examples we'll talk about throughout the course will be modeled with these normal distributions. So it's going to be kind of key that we understand kind of what we're doing here. So the main thing about a normal distribution, there's some notation here. Normal distributions are denoted with a capital N and then a set of parentheses with its two parameters entered in. So the two arguments that a normal distribution needs to work is a mean. Now notice we switched up our notation for mean here. Up until this point, mean was denoted with an X bar. Now it's going to be denoted with the Greek letter mu. Okay? So mean now denoted with a Greek letter mu. So if you see mu in a problem, it's telling you that's the mean of the distribution. Standard deviation has been denoted as an S up until now. Now we're going to start using, or you're going to start seeing this lowercase sigma. Okay, so it's like a little O with a tail at the top there. So mean and standard deviation. Remember yesterday we talked about standardizing scores, calculating z-scores, right? When we calculated z-scores, we said we're going to use standard deviation as our unit of measure. So we're not going to be measuring in terms of weight or inches or anything like that. It's going to be based on standard deviation for the distribution. So this first argument in a normal distribution tells us the center. That's the mean. The second argument will always tell us the standard deviation, the spread. So that's going to tell us kind of how wide or thin our distribution is going to look. Okay? So this is where the steepness in a normal distribution occurs. So when we look at a couple examples here. So a normal distribution has to be symmetric, okay, unimodal, and somewhat bell-shaped. So we have two different normal distributions here. The middle, where the peak is always going to be the mean of the distribution. So that's never going to change. The mean's always going to be right at that center point, right at the peak. Now at this point, like I said, we're using standard deviation to measure distance from the mean. So we're talking about how many standard deviations above or how many standard deviations below the mean we happen to fall. So when you label a normal distribution, and this is something you are going to have to do on your homework, you're going to have to draw a normal distribution, label the mean, and then distribute out the standard deviations. So what you need to look for, one standard deviation on either side of the mean is going to be essentially where the steepness of the hill changes. So generally it's going to be about halfway down the hill. Okay, so where it starts going from very steep to kind of starting to level out, that's about where you want to put one standard deviation. So on the other side here, we'd want the other one somewhere out here in the middle. Okay, so this would be -1 standard deviation out. Alright. Notice in the second normal distribution here, they mark the mean right in the center there, and then in this case they have their standard deviation hitting about close to the middle, maybe a little bit above, but where that steepness kind of starts to change. And for the most part, when you're labeling your standard deviations, as long as you're pretty close, I'm not going to be too big of a stickler. Now, if you're putting your first standard deviation out at the bottom of the hill, I'm going to count that wrong. But as long as you're pretty close to about the right spot marking it, you're going to be okay. All right? Now, let's take a look here. Which of these two distributions has a larger standard deviation? Just based on look. The one on the left, how do we know? Because it's wider. The standard deviation width is wider than on the right side, right? So the side on the left is going to have a wider standard deviation. Now, what do you notice about the heights of the graphs? The one on the right is taller. Why are they different heights? Back to what we know about density curves. Well, so they're different distributions, so they have the same overall shape, but they can have different heights, obviously. But why are the heights different? Not just because they're different, but to make the area equal 1. Remember, inside a density curve, the area underneath has to equal 1. So if this distribution on the left has a wider distribution, that means it's spread out farther along the x-axis, it can't reach as high up on the y-axis then, because the area has to be 1 underneath. On the right side, since the standard deviation is smaller, it's narrower, that means our width is smaller, so the height has to be taller to get that area underneath to be 1. Okay? So again, this just kind of illustrates that point. Inside a density curve, you have to make sure that you know that the area inside is always going to be 1. Okay with that? All right. Here's the big thing. 68, 95, 99, 7 rule. This is the one I have to have you know. Okay, so if you walk out of here knowing nothing else from today, you need to know this. Now the 68, 95, 99, 7 rule applies to every normal curve. It does not matter how wide the standard deviation is. It doesn't matter how tall or short the distribution is. The 68, 95, 99, 7 rule is going to work for every normal distribution. So in the picture there, we have an illustration of what the 68, 95, 99, 7 rule says. So on the x-axis here, okay, we have a normal distribution. Now the mean, they're just saying, is at 0 right now. Now we said from here on, our measurement is going to be in terms of standard deviation. So what they've done here is they've marked out 1 standard deviation above the mean. So notice it's about halfway down the hill. One of the things you might want to make note of is where the 2 standard deviations and 3 standard deviations fall on the normal distribution as well. That's going to be key. Because when you draw out your normal distributions, and we're using the 60, 99, or 95, 99, 7 rule, you have to be able to mark those in correctly. So 1 standard deviation happens about halfway down the hill. 2 standard deviations happens kind of close to the base. And then 3 standard deviations is kind of out in the tail. Okay? And then the same thing happens on the left side where we go in the negative direction. So negative 1 standard deviation about halfway down the hill, negative 2 standard deviations right at the base, and then negative 3 standard deviations kind of out in the tail. Okay? So being able to label these things is going to be important. Now, what the 68, 95, 99, 7 rule actually states, it says for every normal distribution, so anytime you know your distribution is normal, you can guarantee that about 68% of all of your observations will fall within 1 standard deviation of the mean. So if we think about that in terms of relating back to what we know already, when we talked about spread, we talked about an IQR. What was the IQR? The interquartile range, which we calculated by taking Q3 minus Q1, right? Now that represented the middle 50% of our data, right? That said that 50% of our data is going to fall within those two boundaries, the middle 50. Well, the same type of thing applies here with normal distributions, except for instead of the middle 50, we're expanding it out to percentages based on standard deviations. So 68% of all of our data will fall within 1 standard deviation of the mean. 95% of all of our observations will fall within 2 standard deviations of the mean. And then 99.7% of all of our observations will fall within 3 standard deviations of the mean. Now here's where we want to start talking about what these percentages mean. When we look at this curve, these percentages are corresponding to area under the curve. When we calculate, when it asks the question, it says what percentage or what proportion of observations fall above this or below this or between this. Those are going to be the types of questions we answer. What percentage? So what percent of our observations lie within this range of values? Okay? What they're actually asking you to do is calculate the area under the curve. Now, when we get to the point where you guys are calculating actual percentages, you will not have to know calculus and find area under a curve. There's a table that's going to tell you the area. They've already worked it out for all of the main points on a normal distribution. But you're still going to have to know that when you're calculating those percentages, you are calculating an area under the curve. Okay, so 68% of our area is within 1 standard deviation of the mean. 95% of our area is within 2, and then 99.7 is within 3. Okay, so that's what it says. Now let's talk about kind of how to apply that. So here's an example. The length of human pregnancies from conception to birth varies according to a distribution that's approximately normal. It has a mean of 266 days and a standard deviation of 16 days. We're going to use the 68, 95, 99, 7 rule to answer a couple questions about percentages. What percent of pregnancies last this long? Or how long do the longest 2% of pregnancies last? Things like that. Okay? So first thing, always look for the idea of normal distributions. They have to tell you something is normal for you to be able to assume it is. Okay? The other thing, most of the time, you will see this term approximately used with the normal description. And that's because in the real world, data is not always going to be exactly normal. Normal is like if it was perfectly symmetric, everything about it was identical, and that just doesn't happen, okay? So when you say something has a normal distribution, you're basically saying it's approximately normal. It's close to, but may not be exactly like it, okay? So be aware of that. The next thing is being able to pick out your mean and your standard deviation, okay? So what we have here is a normal distribution that has a mean of 266 days and a standard deviation of 16. So you might see them report a normal distribution in this manner. So the capital N tells you it's normal, the first argument tells you your mean, the second argument tells you your standard deviation. Okay? So the first thing, anytime they tell you to use the 68, 95, 99, 7 rule, the first thing you're going to have to do is draw a picture. You're going to have to draw a normal distribution and mark it with its mean, and then mark out its standard deviations on each side of the mean. So, when we're looking at a problem like this, the first thing we're going to do is sketch our normal distribution. And for the most part, just try to be kind of as close as you can. So it's another one of those things, I don't expect you guys to draw these perfectly. I don't draw them perfectly hardly ever. Okay? So just come as close as you can. Make it as symmetric as possible. Make the nice tails on each end. Okay? So what we're going to do here is we're going to mark our mean and standard deviations. So our mean, we're going to mark right in the middle of our distribution. So what is our mean? 266. Okay? Now, when we go to mark our standard deviations, what I tend to do is I go ahead and make the marks first. Make sure I have the markings in the correct spot. So if we go about halfway down the hill, we can mark one standard deviation about there. 2 standard deviations happens about at the bottom of the hill. And then 3 standard deviations is going to fall kind of out in the tail. Okay? So this would correspond to 1 standard deviation, this would be 2 standard deviations, and then this would be 3. And then you need to do the same thing on the negative side. So about halfway down the hill, we're going to mark -1 standard deviations. 2 happens kind of at the base of the hill, and then 3 kind of out in the tail. Okay? But for our types of problems, this 1 standard deviation, 2 standard deviations, 3 standard deviations doesn't really mean much to us. We need actual values. Okay? So here's where knowing the standard deviation comes into play. Our mean's at 266. My standard deviation is 16. Right? So if I go 1 standard deviation above the mean, so if I go exactly 1 standard deviation above, what value would that correspond to? 282, right? It's the 16 plus our mean. So 266 days is the mean. If I go 1 standard deviation above, I need to add 16 days, because standard deviation is now my ruler, and my ruler goes by 16 days now at this point. So I'd go to 282 for 1 standard deviation above the mean. And then we have 2 standard deviations above the mean. So now I'm going to have to take 282 and add another 16, so 298. And then if I want 3 standard deviations, add 16 again, so 314. So 282 days would be exactly 1 standard deviation above our mean value. 298 would be exactly 2 standard deviations above, and so on. Now when we go in the opposite direction, instead of adding, we need to subtract. So for 1 standard deviation below the mean, it would be 250. 2 standard deviations below the mean, 234. And then 3 standard deviations below, 218. So the first thing you're going to have to do with each of these problems is sketch and label your normal distribution. So mark your mean in the middle, add your standard deviation, whatever happens to be for the problem, all the way up to 3, and then subtract your standard deviation all the way down to 3. So get that labeling down first. That's the first part. Okay? So that's our first step. Oops, I'm going to lose my picture here. So you guys all have the picture drawn? Okay, so I'm going to go ahead and erase this because it's going to disappear anyway. Alright, so between what values do the lengths of the middle 99.7% of all pregnancies fall? So here was our distribution. Okay, we want the middle 99.7%. So look back at the rule, 68, 95, 99.7. The 99.7% corresponded to what? 3 standard deviations, right? So the rule said 99.7% of all values fall within 3 standard deviations of the mean. So if I want the middle 99.7% of all pregnancies, I want my cutoffs at 3 standard deviations, right? So the middle 99.7% of all pregnancies lie between 218 and 314 days. So 99.7% of all pregnancies are going to last between 218 and 314 days. Does that make sense? Okay. Here's the next one. So how short are the shortest 2.5% of all pregnancies? So think about this. Do we see a 2.5 anywhere in the rule? No. Now what we do know, within 1 standard deviation, we've got 68%, right? Within 2 standard deviations, we've got 95%. And within 3 standard deviations, we have 99.7%. Well, those are only telling us what's inside, right? So like when I say 68% is within 1 standard deviation, what percent of values would be outside 1 standard deviation? $32, right? So we'd have 32 total percent outside of 1 standard deviation, okay? But I have 2 different sides here. So if I have 32 total percent, how much percentage, or what percentage would I have on the outside on each side? 16. Since the normal distribution is perfectly symmetric, that means out here, I have 16%. And then out this way, I have 16%. Okay? Let's look at the next one. If I have 95 total percent inside of 2 standard deviations, what percent of observations would fall outside of 2 standard deviations? 5 total percent. How much for each side? 2.5. So I have 2.5% out here and 2.5% out here. Right? For 99.7%, if I have 99.7% in, what percent would lie outside 3? 0.3%, right? So that would mean 0.15% here and 0.15% here. Okay? So we're not always going to be interested in the middle. We might sometimes be interested in the tails. So for instance here, how short are the shortest 2.5% of all pregnancies? Here's my 2.5%. Goes with that 95. So what I need to figure out is 2.5% goes with 2 standard deviations, so 234. So anything less than 234 days would be considered the shortest 2.5%. So part of what you're going to be expected to do with this 68, 95, 99, 7 rule is manipulate some of these percentages. So you know where the middles fall. We just now discussed where the outsides fall. You may have to do some type of combination with them, but knowing the percentages, it's just a matter of manipulating them and figuring out where you are. Okay? So the shortest 2.5%, less than 234 days. Okay there? All right. What percent of pregnancies last between 266 and 282 days? Okay. So between 266 and 282 days. So on these types of problems where they give us values to start and we have to come up with the percentage, we need to look at what area we're talking about. So 266 to 282 is this area right here. Okay? So think about where we're at in terms of our overall distribution. One of our endpoints is at the mean. The other endpoint is at 1 standard deviation above the mean. Okay? Now, what percentage do we associate with 1 standard deviation? 68%. So 68% goes from negative 1 standard deviation to positive 1 standard deviation. But if I'm stopping myself at the mean and only looking at this right portion, so from 0 to 1 standard deviation, what percent would I be looking at? 34%. I'm only looking at half of that particular interval. So 34% of all pregnancies would last between 266 days and 282 days. Does that make sense? So if you're stopping yourself at the mean and going out in either direction to a specific standard deviation, take what the rule tells you and cut it in half. Okay? Let's take a look at this next one. So what percent of pregnancies last between 218 days and 234 days? So here's what we're looking at right now, 218 and 234. .5% would be left of this one, right? So very good. The first thing we have to recognize is this is 2 standard deviations, which means 2.5% lies left of that one. Now, that 2.5% though reaches till the very end of our distribution. So 2.5% all the way to the end. We're cutting ourselves off at 218, right? So think about from 218, how much would have been left from there? What was that percent we calculated for outside of 3 standard deviations? 0.3 for the total, which meant 0.15 for just one side, right? So think about this. From here all the way left, we have 2.5%, right? From 3 all the way left, we have 0.15%. Now this is an amount we don't want. That's an amount that we're not accounting for, right? So I need to take my 2.5% and subtract out the area I don't want, the 0.15. So you get about 2.35% of all pregnancies. So when you get this type of problem where you're looking between two values, it might not be as simple as cutting the overall in half. So in that case, pick your farthest right spot. So in this case, the 234. Find the percent of values left of that point. So how much of your distribution is left of that particular point? Then find your cutoff point on the left. Find out how much is left of that. So if you find the two left percentages, all you have to do is subtract them. Big minus small, that's going to leave you what's with or what in between. Everyone kind of follow that? So if you can find the area, the total area left of a point, and then a total area of the next point, subtract the two, you'll get what's left in between them. Okay? So that's it for today. Now, it's going to be extremely important for you guys to make sure you practice this 68, 95, 99, 7 rule. Some of those last examples can get tricky when they start mixing up the different percentages and they start mixing up the cutoff points. Okay, so it's all about figuring out percentages. What percent are we actually talking about? And then manipulating it for that. So over the weekend, besides finishing up page 99, I want you to start working through page 128 here. There's not a lot of problems, so hopefully it doesn't take you too long. 33 through 35 is going to deal with just density curves in general. So just general questions about density curves. And then 40 through 44 are going to start talking about normal distributions, the 68, 95, 99, 7 rule, and things like that. Okay? So try those out. The answer key for this will be up later today. So over the weekend as you're working, you can get access to that on the blog and check what you're doing. Okay? Yeah.